as we work through this development, we also took one step back to look at what are the common failure modes of plastics in general. Did it fit with the failure modes we were seeing at these extreme conditions? And then also, as a result of that, also build that into the systems that we were developing. So you can see here, this is from a textbook on failure analysis. You can see almost 60% of your failures in the field for plastics come down to chemical resistance or creep. So in downhole service, and I would also say would look likely in electrolyzers, fuel cells, and hydrogen, is the chemical resistance can limit some of the high temperature polymers or high strength polymers that you might be familiar with. Polyimides, BMIs, epoxies, they show poor hydrolysis resistance. So in wells where there is any exposure to moisture, that would be a big problem. And also in fuel cells where you might have wet hydrogen or exposure to water at temperature, you can have a lot of issues there. And then also creep. We were talking about creep at ultra high temperatures, but creep at long times, if you're talking about a lifetime of a year or longer, you can have similar kind of creep failures at lower temperature, below TG, as you have at high temperature in a shorter time period. And again, the higher temperatures and higher pressures will increase the degree of creep. So really these two factors as main points of attack for our material development, we use that as a basis for some of the activities that we followed.